All right, so here we are, Calc 30. Page 46 is in the Red Stewart calculus text here. Calculus, the first course, Red Stewart text. This is your text here, and it's starting on page, looks like 46. So infinite limits. All right, let's talk about, first of all, the title, infinite limits. We know about limits. We've been studying limits the whole chapter. Okay, as x approaches a certain value, what does the responding function, what value does the function yield, right? So if y equals x, as x approaches 5, y approaches 5, right? As close as we get to 5, y is going to get to 5. If y equals x squared, then as x approaches 5, then y approaches 5 squared, or 25. So you know about limits. We just got finished doing a question 1.5 that was a real tricky question, lots of algebra involved, things like that. So this was it here. Okay, so we can use limits to find instantaneous rates of change as x, or the variable, approaches a certain value. But what happens if we have the variable, in this case n, in this example, approaching infinity? Okay, so infinity is not a number. It's not a value you can write down on a piece of paper. Infinity is more of a concept. So what this is saying is, what is happening to the function, and the function will always be written right here, as the variable that's in that function gets larger and larger and larger and larger without any boundary. It just keeps getting larger and larger. What does the function end up doing? So there's different things that functions could end up doing. For example, in this function, if the function is just n by itself, okay, then what happens is, like let's say that if n is 5, okay, then n is 5. If n is 10, then n is 10. So it just kind of keeps going up forever and ever. The value, as n increases, the function named just n also increases. So this approaches infinity. As n approaches infinity, the function n approaches infinity, okay? Now what happens if we have 2n, let's say? So the function is 2n. So if n is, let's say, 5, then the value is 10, okay? And if n is 100, if n travels along to infinity, when n is 100, this function is 200. When n is 1 billion, this function yields a value of 2 billion. So this approaches infinity as well. It just goes at a little steeper rate. The slope of that line is now 2, but it still goes to infinity. Okay. All right, so what happens if this number is, let's say, 1/2? Oh, okay, 1/2. Well, as n approaches infinity, let's say n gets to 5, well, the value then will be 2.5. As n gets larger, if n is 10, then the value is 5. If n is 100, the value of 1/2 n is 50. So notice that 2.5, 5, 50, they're still getting larger and larger as n gets larger. So we have a slope that is 1/2, but we still have a line that is getting higher and higher and higher, larger and larger and larger as n gets larger. So in some cases, the function will react, and that's, if you remember in pre-calc 30, when we talked about end behavior. Do you remember about end behavior? So if you have a function that has an end behavior as x approaches, it gets larger and larger, approaches infinity. Let's say for a parabola, you see the parabola? It goes up if it opens upwards. As x gets larger, the value of the function gets larger and larger. So there's lots of examples where the function approaches infinity. Now, if you have something like this, 1 over n, now that's very curious, and this is a very special limit that we are going to take advantage of when we're finding limits of more complicated functions. So this is the first very important thing. If you haven't written this down yet, it's a good idea to write kind of this down, is the limit of n as n approaches infinity is infinity. But this one right here is our first major breakthrough here. So what happens here is as n gets larger, let's say n is 2. Well, the value of this function is 1 over 2, right? As n gets larger, let's say it's 10. The value of this is 1 over 10. If n is 100, our value of our function is 1 over 100. And as you see, 1 over 1,000 and so on, as you see what's happening to these values, well, these values are getting smaller and smaller and smaller, and they're getting closer and closer to 0. You see? Think about 1 over 10,000, 1 over a million, 1 over a billion, 1 over a trillion. So 1 trillionth is very, very small, close to 0. So this is sort of the graph that happens. If you fill in all the values, you have a graph that looks like this. And notice as x approaches infinity, here's just up to 13, you see that? But if this was a billion, this point would be so close to 0, it would be imperceptibly far from 0. It would be so close, it would look like it's touching. But 1 over a billion is still not 0, so it's not actually 0, but it's very, very, very close to 0. So what we can say is this very important thing. The limit of a function where n approaches infinity, and the function is 1 over n. This limit, or the value that this function would approach, would be 0. Okay, you see these points are getting closer and closer and closer to the y equals 0. They'll never touch 0, they'll never pass 0, but they will get infinitely close to 0. So this is super, super important. Okay, very, very important. We're going to need to use this one. It also should be noted that if we have an exponent on this function, and we just name that exponent r, as long as r is greater than 1, then this limit still holds true. So you can write this down as well with this kind of caveat here. But these numbers like 1/2, if this was to the power of 2, 1/2 would be 1/4, and 1/10 would be 1/100th, and 1, and so on. And so these numbers still go down to 0. They just get down to 0 quicker. Okay, so you see like this, like these, they go down and they get closer to 0 quicker. So you can have an exponent there. That's also extremely important for this section. All right. Okay, so here's a couple examples that I want to show you here. The limit of 2x squared as x approaches infinity. Okay, now notice that this x here is not kind of a 1 over x, right? It's not a 1 over x, it's just kind of a regular x squared. So as x gets larger, the value of 2x squared also gets larger, right? It increases without bound, and so the limit is infinity. The value of this function, as x gets larger, the value of the function also gets larger. But with this one, not so much. All right? 15 over n. Now, this 15, okay, I want you to watch. This actually can be written also as the limit as n approaches infinity of 15 times 1 over n. Okay? So you see a 1 over n there. Now, according to our limit rules, as we've learned, and I will review these rules again too in this lesson, hopefully, this 15 actually, because there's no variable attached to it, it can actually come out in front of the limit. So this is actually 15 times the limit as n approaches infinity of 1 over n. So 15 can move right outside and be a multiplier there because there's no n involved, so 15 will never change. As n changes, the number 15 will never change. So as a product, it can go out here as a factor. So do you see what's happening here now? As I take this limit right here, as n approaches infinity, 1 over n becomes what? Becomes 0. So this actually is 15 times 0. The limit is 0. So it doesn't matter what scalar numbers on top of here either, this will still approach 0, because if you think about it with the 15 on there, 15 over 1 is 15. 15 over 10 is 1.5. 15 over 100, right, as n gets bigger. Now we start to get to 0.15, and then you can see this gets smaller and smaller, and even though there's a 15 up there, 15 over a trillion is really close to 0, right? If you got 15 marks out of a possible trillion marks on an exam, first of all, that exam would be very long, but you would have pretty close to 0% if you only got 15 out of a trillion marks. Does that make sense? So it doesn't matter what number's on top here. If n truly does go to infinity, then that number becomes insignificant. You still have a limit of 0. Okay? Now this is hard to wrap your brain around, I understand. When we start talking about infinity, it's hard to wrap your brain around because we are finite people. Our brains are finite, but we can imagine infinity, and that's what we want to do. We want to kind of like extend, we want to like look past all of the numbers that we can find and see what happens if we were to go further and further and further. Now, this is the crux of this lesson. crux meaning the most important part. So infinite limits on rational functions is where all of this is very important, okay? So we are going to use this right here. This is what we just talked about. We are going to have to use this property of limits in figuring this limit out. So here's our true example. Here's our example right here. The limit as n approaches infinity of the function n squared minus n over 2n squared plus 1. Now, what you don't want to do is this. Don't write this down. You don't have to write this down, but this is what you don't want to do. You don't want to say, oh, I am going to use my properties of limits, which I think you guys have seen before. They're down here that I clipped from your textbook. I think they're on page, 13 or something. Some of these properties of limits. But in a rational function, okay, so you can take, you see the function up here, right? You can actually apply the limit separately to the function on the top and the function on the bottom. And if you have additional parts, you can apply the limit to each additional part as well, or subtractional part, okay? So what that means is that you can actually apply the limit separately to each one of these, okay? You can. Now, you're going to run into trouble if you do this, because what is this? Well, that's infinity. What is this one? Oh, that's infinity. What is this one down here? Well, that's 2 times infinity. And what's this one? Plus 1. Okay. So if you just substitute your ideas of what happens when n gets large, you have infinity plus infinity divided by 2 times infinity plus 1. This makes no sense at all. It's meaningless. So you cannot just sort of substitute infinity in for the variable like that, okay? So that's meaningless. That does not work at all. We can't do that just yet. But what we can do is make use of this property right here, and I'm going to show you how we're going to do that, okay? So instead of applying the limits just yet, we are going to have to do something else first. So what we're going to do is we are going to, now I don't know if I have steps written out here for you or not. Not exactly. Oh, come on now, computer. Computer's sleepy this morning. Okay. So what we're going to do is we are going to, and you did this in Pre-Cal 30, right? When we did, well, we did all sorts of manipulations of rational expressions in proving identities, okay? Now, proving identities often is a sore spot for a lot of calculus students, and maybe not your favorite part of Pre-Cal 30. But the importance here is that we can actually rewrite rational expressions so that they exist in different forms, okay? For example, 1 over 2 is actually equal to 4 over 8, right? So I've actually multiplied 4 times the top and the bottom without changing the value of this. I've just expressed it in a different way, okay? So that's an example. And what we're going to do here is I am going to look at my my variable, all the variable terms here, and I'm going to examine what is the largest exponent on any of the variables, and I see that it's a 2, okay? So what I'm going to do is I am going to now multiply, and again, I usually talk later in terms of division, but what I'm going to do is I'm going to multiply top and bottom by the same thing, so I'm not going to change the actual rational function, but what I'm going to do is I'm going to multiply the top and the bottom by 1 over n squared. 1 over n squared. Okay? So you take the variable with the largest exponent, and that's what you sort of divide each term by that. Okay? So this is what it looks like now. Okay? The limit as n approaches infinity, I'm going to have n squared over n squared minus n over n squared all over 2n squared divided by n squared plus 1 over n squared. So instead of adding or subtracting, two rationals, sorry, trying to get this out this morning, I'm breaking them apart, right? And I'm making a common denominator. And so if you do this, watch what happens. What ends up simplifying out here is this. This n squared divided by n squared is actually just 1. This is actually 1 over n when you simplify that, right? The n goes with one of those n's on the bottom. this is actually just a 2. And this is, again, 1 over n squared, or 1 over n. You can say all squared if you want, but I'll write it like this because we've seen this already. Now what's important is that we see is that now I actually can apply these limits. This limit I can apply to each term, and I won't get an infinity anymore. Okay? I'm not going to get an infinity. So again, I'm going to write all this out. You're not going to have to write every step out completely like this, but I'm going to write this all out so you can see it. This top part of the rational is going to be limit as n approaches infinity of 1 minus, I'm going to apply that limit to this term as well, limit as n approaches infinity of 1 over n, which is excellent. We've seen that before. This is the limit as n approaches infinity of 2 plus the limit as n approaches infinity of 1 over n all squared. Okay. Now, as n approaches infinity for the function y equals 1, okay, for 1. Remember that's a line right here. That's a horizontal line that goes through y equals 1, right? And so as n approaches infinity, what happens to the function y equals 1? It becomes what? So when n is 5, this function is 1. When n is 10, this function is 1. When n is a billion, this function is 1. So because there's no variable here, it's just a number 1, as n changes, this does not change. It doesn't affect this at all. So this, as n approaches infinity, this approaches a limit of 1. It just stays as 1. Same down here. Look at this. As n approaches infinity, the value 2 stays as a 2, okay? So that's a 1, that's 2. No, I don't. Yeah. And I think that's best explained by the graph here, right? Like it's a horizontal line, so as n gets bigger, the line does not change. It just stays as the value. Now this one, as n approaches infinity, 1 over n becomes what? 0. And as n approaches infinity of 1 over n squared, that just approaches 0 a little bit quicker. So that approaches 0 as well. So now what I have, this is amazing, I have 1 minus 0 over 2 plus 0. So the limit actually is 1 over 2. It's 1/2. So it's not infinity plus infinity divided by 2 times infinity plus 0, right? Remember? That doesn't make any sense. If we do it this way, we can see that the limit is actually 1/2. We wouldn't see that unless we did this method. Okay, any questions about that? Because I'm going to do another example here for you. But any questions about this at all? Okay, let's do another example. All right, let's do this example here. This is, I think, from your assignment. So this is a question from your assignment that I'll do with you. Let's see, is this 12A? No, wait. 6. Okay, I don't know where this is from. This is not in 1.6. This might be in a review assignment or something. Let's see. Oh yeah, it's from the review assignment. So this is 12A in your review assignment. Okay, so again, we can apply the limit to each separate term if that makes sense to do that, and we can. So this is the shortcut now that you can do to show your work, okay? So you can just go like this. You can say, hey, as the limit as n approaches infinity of 2, that actually approaches, and you can just do those double lines like I did, that approaches 2. All right, put a little arrow there if you want. The limit as n approaches infinity of this term, that approaches 0. This, the limit as n approaches infinity, this approaches 3 times 1 over n squared, which is 3 times 0, or 0. Remember, the number on top doesn't affect what that approaches. So what do we have? We have, as n approaches infinity, this term approaches 2, this term approaches 0, and this term approaches 0. So my limit is 2. Good? Now you can confirm, I won't take the time to do this, you can confirm by graphing this. Okay, and what you will find is that the graph, whatever it does here, okay, it will, I don't know I don't know what this one looks like, to be honest with you. But it could be, it could kind of like come up like this, and then at the end, the further you go to the right, it'll start to flatten out. And this asymptote right here that it will start to approach, the horizontal asymptote, will be 2. So if you're graphing this stuff, then zoom way over till you get to like n equals or x equals 100 or 1,000 or something, and find out if the graph is starting to get flat and what value that is that it's starting to approach. Okay? All right, let's do one more example from your assignments here. Okay, let's do this one. This one's 2e. No, 3e. It's 3e from your assignment. So it says, what's the limit as n approaches infinity of the function 6n plus 9 over 3n minus 2? Okay? So what we do is we look at, hey, what's the largest exponent on any of the variable terms here? And it's certainly just a 1, right? So what I'm going to do is I'm going to, and this is what you can do as well, you can just write, I'm going to divide by n. Every term I'm going to divide by n. That's the same as multiplying by 1 over n here. I'm going to divide by n, I'm going to divide by n. Every single term. One more step that you should show is what is the simplification of this now. So 6n over n is 6 plus 9 over n. 3n over n is just 3 minus 2 over n. Now that when I apply the limit to each single term, I'm not going to get infinity anywhere. So I can just write out what it is that I get with my little lines here. That's going to be 6. This is going to be 0. That's going to be 3. And this is going to be 0. So I end up with 6 plus 0 on top and 3 minus 0 on the bottom, which is 6 over 3 or 2. And this one I will just show you quickly the graph so we can double check this, okay? All right, so if I graph this and I look at the graph, what I'm interested in is x approaches infinity. So look at as I get, now this is only at 80, 100. You see how this line is already flattening out? Okay, so let's just see what these values look like. Oh, look at, what are they getting close to? The y value of 2. See, right now it's at 2.021. Now it's at 0.19. Now it's at 0, right? As you go on further and further, you can actually just sort of test this. And if I change my x-axis to go all the way to, let's say, 11,000 or something, then look what happens here. Look at that, very close to 2. You see that? And there's some point where the computer just says, hey, that's pretty much 2. We're infinitely close to 2, okay? So everybody see that? Yeah? Look good? Okay, so that's your proof there that works. And again, these type of questions are going to be on 1.6 and your review 1.8, I believe. So that's the end of the lesson here. If you want to take a look at your assignment here now. Actually, I'm going to go to the website to double check.